So, welcome back. This is continuation of what we were doing. So, we had to look at the input and output impedance of the common source amplifier. Okay, I am not going to solve this fully, but I will just give you an idea of what we should do, and it is fairly straightforward as to how you can find out. Okay. So, if I draw the incremental circuit, what do I have in the incremental circuit? I have a small signal source, I have my RS, so this is Vs, I have RS, then what do I have? I have my RA parallel RB, correct? Then that goes there. Similarly, on the outside I have a current source. The current source value is GM VGS, this plus minus is VGS, correct? On the output I have, what is my output? This is my RD, correct? Then I have my, if I assume that I have a lambda, then I have an RDS, correct? And I have my RL, and that is my V out. This is assuming that all the capacitors are shorts. Okay. So, now if I want the input impedance, what is the impedance that I have to look for? Now, where is my amplifier actually? Which is the amplifier? Which is the boundary of the amplifier? That is my amplifier, right? So, what is my input impedance? Impedance is the impedance looking in here. So, I will call it as Z in, correct? And what is the impedance? Our impedance is the impedance looking like that, correct? So, in general, if I have a network, right, this is again back to what we did in the previous course. If I have some network, network has some resistor, inductors, capacitors, and some sources, say some voltage control source, so on, so forth. Okay, and these dependent sources, and say you have some independent voltage source. So, say I have to find out my input impedance and output impedance. How would you do this problem? Say I want to find out what in. How do you solve it? Can someone tell me? Oops. So, this is the procedure. What do you do basically? Thevenin is, but what is the most general way of doing it? Exactly. So, I can this with a V test, correct? And what should I do to things inside here? I should kill what? All my independent sources. My independent sources should go. What about voltage control source? They will remain, and basically values they take will now become functions of V test. Okay. And then you have to find out what do you do about the output port. Should you? Not necessarily, leave it open, right? Don't do anything here. If then that RL will be there, but don't do anything special port, correct? So, I will write here, I will say nothing special. And what is the value of my Z in? Z in becomes basically equal to So that is your V test, and I say that some I test flows, then my Z in is V test divided I test. Correct? This is the procedure. Similarly, Z out. What will you do out? I'll take, and then I'm again going to energize with a some V test. Measure what current is flowing, call the I test. Right? Now special here. Right? And if I am going to say this is my Z out, and Z out is nothing but my test divided by test. Correct? So that is your procedure. Calculate the in and Z out when you have a network which has both passive components and active components, which could either be independent sources or dependent sources. So basically you have all the independent sources. And what dependent sources are? Dependent sources continue to survive if the controlling element is a non-zero value. If the controlling element becomes a zero value, then the dependent source also dies. Okay? We have done many examples of this in the first course. So what I will ask you to do is basically do that and find out the input impedance and impedance of this. Correct? Actually, you can look and tell me by inspection, but just work it out. Okay? So okay, so basically find out what is Z and find out what is Z out. Right? This is very straightforward. I'm not going to see here. You can work it out. Okay? Any questions? No. We have done a lot of these things in the previous. Okay. All right. So now let's go to next topic of analysis, which is the frequency response. Frequency response. Okay. Now, before we go there, we should understand what are the various capacitors that are there in the strip. So far, what are the capacitors that we have looked at? Right, we have looked at the coupling capacitors. For the purpose of this analysis, we will assume that these are short circuits. The analysis will become already very messy. Assume that these are short circuits for this analysis. What we are actually going to see is actually the high frequency response of the amplifier. These coupling capacitors, what do they determine? What the coupling capacitors determine? Correct. So the coupling capacitors did low frequency response. Want to say something is DC and something is AC. Correct. So you can have a situation such that, right, there might be a situation like where right, maybe your cutoff frequency omega in cutoff. What does this mean? It means that everything that is higher this will be coupled to the amplifier. I'll tell you. And what is in this region will be blocked. just to see that, let's go back and see about the frequency response. Say for example the input frequency response, right? What was the input frequency response? It was like this. It was j omega c. We in fact wrote it down here. It was a j omega by omega 1 divided by 1 plus omega by omega 2. If your RS is very small, right, which is a reasonable thing to say, RA parallel RB is much greater than RS. That's how we are designing this, which means that this omega 1 is approximately omega 2. So what is this response like? Is this a low pass filter or a high pass filter? Right? Why do you say that? At I equal to 0. So assume that this is that, okay, which is approximately equal to 1 plus j omega 1 divided by 1 plus, sorry, right? When is this the case? When I parallel R is greater than RS. Correct? Now at omega less than omega 1, how will this look? If omega is less than omega 1, you drop omega by 1 with respect to 1. So you will just have an omega by omega 1. So you are going to have a degree per decade rise, right? So that, and then for omega much greater than omega, what will happen? You drop the 1 with respect to the j omega by omega 1, all of them become 1. So basically this frequency response will be, the frequency response will go up like, and then it will be flat and be your 1. Correct? What am I plotting here? On this side, and on this side I am plotting modulus of VGS divided by Vs. So here what is happening? It's basically telling any signal which is greater than omega 1 will get coupled to the input, will go into the small signal circuit, and anything less than omega 1 will be blocked. So say you want to make an amplifier that's going to amplify signals above 1 kilohertz. That means anything below 1 kilohertz you can block. So you will set your omega 1 to around 1 kilohertz. So anything above 1 kilohertz will be coupled to the amplifier. Anything below 1 kilohertz will be killed. Okay. So basically this C1 capacitor is acting like a high pass filter. What C2 capacitor? What about C2? If you look at 2, right, what is the response you are supposed to look at? You have to look at this response, right? This V0 VGS. Again you have a similar kind of high pass response. So again, depending on what this omega 1 here, let's call this omega 2. Omega 2 is going to be 1 by RL C2. So that is going to determine what is your response. So basically what the short story of all of that is that the coupling capacitors essentially determine the low frequency response. So they did what is this omega in cutoff, and similarly you can have possibly an omega out cutoff, right? And you would, the net response of the amplifier be determined by whichever omega 1 and omega 2, whichever is small, right? So I can draw this here like that, and now just to things, let me say I just move a little bit, okay, and let me call this as omega. This would be a very bad way of designing it, right? Because I want to, let me not W then, no, let me, why would you want to take, why would you put an input filter, want to amplify a 1 kilohertz signal, right? Why would you have a situation where your input you are going to filter out everything below 1 kilohertz, but on the output say you are going to filter out everything below 2 kilohertz? Doesn't make sense, right? The signal is going to be at the same frequency. So essentially omega in cutoff and omega out cutoff will be determined by coupling capacitors. Okay, we have finished the coupling capacitors. So for now, let us that we are not worried about the coupling capacitors, and let's only look at the other capacitances that are there in the circuit. Yes, correct. Because by low frequency, what I mean is that things which are less than this cut frequency are cut out. They work in high frequencies. The same thing, you are understanding it in a different way. So basically these things cut off your DC, right? For frequencies which are more than this cutoff, they don't trouble the system. So in a way, it's trouble things at low frequency. So in my mind, I am calling that the low frequency response. As long as you understand what is happening, it is okay. It is just terminology. It may be bad terminology also. Okay. All right. Now let's move to the capacitors in the circuit. And to understand the other capacitors in the circuit, it's important to look at the MOSFET again. Okay. Now I'm going to look at the MOSFET capacitances. So remember, we do the MOSFET as something like this, right? We source and drain region and a bulk. So I call this, for example, doped P. I call this N. I call that N plus. Don't worry about these things. But just to have an idea where these capacitances are coming from. Okay. Then what else do I have? I have a gate, right? So the usually is made overlap a bit of the source and the drain, because you do not want to break in the channel. So it's better to compensate on the other. So the gate usually overlaps the source and drain a little bit. So it's this overlap region, right? Can you see the overlap is given by, right? If you see that, there's an overlap, right? All right. This is your gate. Then semiconductor, no. So that is your oxide. This is my oxide. On top of the oxide is going to sit the metal. So is your metal. And the gate contact is here. What about the other two contacts? You contact here for the source and you contact here for the drain. Okay. And what is the bottom terminal called? Substrate or bulk. We didn't worry about the bulk. But from your digital electronics lab, you remember that the bulk is also they have to take care of it, right? So what did we do? We had this symbol like that. So far we are only worrying about the things. So we have drawn gate, drain and source. You also have, right? The bulk was drawn and the bulk had an arrow, something like that, right? And in digital electronics course, what did you do? You connected bulk to the source, right? So in general, the bulk not be connected to the source. So let us not have that. Okay. For this particular course, we are not going to worry about the bulk. We will worry about the bulk in a subsequent course. For now, just be aware that there is a terminal. Okay.
So doesn't the bulk affect whatever you have done?
It does, but when you, for example, if you tie it to source, it will not. What happens is that the bulk causes something called as the effect. It will change the of that threshold voltage, Vt. Okay, but effectively, I have not told you how to estimate Vt and the device structure, right? We have not done that here. So it will go into what that Vt expression will have. So effectively for you, all of that goes into Vt, you don't need to worry about it. Okay. So however, lots of capacitance is here. You remember that in all of this, you're keeping the source as the common terminal. So most of the times you refer to things with respect to the source. What are the capacitances you can associate? So there is a capacitance here, right, which is the capacitance of source to bulk. Capacitance is called SB. Similarly, there is a capacitor. There is a capacitance of bulk. Okay, what do you have?
Metal oxide.
Correct. Now the metal oxide capacitance is usually with respect to this channel, right? So this is a capacitance. Right? You don't have access to this intermediate terminal. So what happens is that people don't put that capacitance there. Instead, so he just change the color of that to blue. Okay. So that capacitance is not considered there. Instead, what they do is to actually write it as the components. One component which is going like that here, and they call capacitance as E. Can you tell me? E, S, and similarly, another extension goes C, G. Okay. So if you have to draw those capacitors, how will they look? Capacitance going from here to here. That is capacitance CGD. I have capacitance going back to here. This capacitance is CS. Then what else do I have? Let me just draw the bulk a little. What other capacitors I have? I have a capacitance from drain to bulk C, and I have a capacitor from bulk source, call that as C LD. Okay. Now the important thing to note is that all of the capacitors not really to bulk, because what's happening is that there is an inversion layer here. This capacitor, so this device has holes, right? When the device is on, when it's in saturation, it actually created a channel of electrons here, called an inversion region. So this blue capacitor is actually going from that gate to that inversion region, and you don't really have a contact to that inversion region. The contact to that inversion is through the two side contacts, either through the source contact or through the drain contact. Then you can't really, it's difficult to access that internal capacitance, so people break it up into this CGS and CD. Okay. So going back, all of these capacitors are functions of bias, and it's really messy. However, for the purpose of this course, we can do the following, and these approximations are good enough. For this course, your CGS is assumed to be much greater than the other capacitors, CDB, CSB and CGD.
So is it the case always?
This is in saturation. Okay, when the device is in saturation, which you are interested, this is out, and all of these things are up equal. Okay, and also can give a value for CGS. CGS is approximately thirds WL ox. What are the units of CS? It's farad per micrometer squared. The Cox is a capacitance per unit area, remember that. So capacitance per unit area into W into L will give you what is the full capacitance. Thirds is a matter of detail, not worry about. Okay. So because these capacitors are all a function of bias, value of these capacitors that go into the incremental circuit will be a function of the bias set up by the bias circuit. Right? Just how we had when we replaced the MOSFET with a voltage controlled source, the value of the GM was a function of where you biased it. If you biased it in linear, you got 1 GM, a very bad GM. Biased it in saturation, you got a good GM, high value of GM. Correct? So similarly, all these capacitors are function of bias. But for this particular course, we will make some simplifications and proceed. Because as you see, even with these simplifications, it is fairly messy. Okay, we are going to do fairly deep analysis. It will give us a very, very involved expression, but then look at that expression and see how we can understand it. And in the process of understanding it, there will be a few things which will be the key takeaways. And what I will require you to remember are those key takeaways. No one will ask you to derive the full frequency of a MOSFET. You will not use it in your design also, because for these kind of things, you use the simulator to simulate it. Because the simulator will know how these capacitors vary as a function of bias and all of that, right? So for the purpose of hand calculation, you don't know all of the details. However, some key takeaways which you should remember. That's what we are trying to go. That's what we are trying to approach. But we are going to do it the dirty way of actually deriving everything. Okay, and it's good practice for algebra. All right. Okay, I take this as my. Let's take it and it will become clear. Now let me just this here, and okay, now let's look at signal amplifier. Let's look at the incremental circuit of the common source amplifier, which we already have, and then let's try and put all these comps in there. Okay, So what did we have as the incremental circuit? We have buying this many times, so you should know. I have a source Vs, I have some Rs. Okay. Now I have RB. Okay. On the other side, what do I have? Nice GM, that is GM, VGS, and then it get connected to my RD, and then I have an RZ, and then I have an RL, and that is my 0. Okay. Now all of this is fairly messy, and as Shubhangi pointed out, we can do some simplifications, right, because we don't want to work with very messy setup. Now if I take this thing I put in a box, right, for all practical purpose I can replace all this in a box by what? I can replace it with some other voltage source. I am not it as a Vs prime, leave it as Vs, right, and some value of S. Okay, for let me just put it like that, Vs prime, S prime, but for subsequent analysis I will the primes. Okay. Similarly, what can you do for the right hand side? All of that, right? All of that can be replaced by what? Single value of resistor, and in principle I should call it as some, right, I should call the resistor as some RL prime, but in order to keep my notation clean I am just going to as RL. Okay. So effectively what happens? Let me again keep this here. So the equivalent circuit that we have now, right, just to convey the point, I am going to draw it with value of and Rs. Keep in mind that this Vs and Rs are the effective Thevenin voltages and the effective Thevenin resistance. Now because your RL RB is much greater than Rs, effectively your Rs prime will be approximately Rs and your Vs prime is approximately S, right, because you have designed it such. So you don't need to really worry. And so these two things go in here. On the output side of my, I have GM, VGS, and over here you have to be careful, there is some value of RL. This is the effective load. However, in this side I am just drawing it as RL because I don't want to mess my notation. You will find it's already very messy. Okay. Now what terminals here? This is connected, right? So this entire thing is the source terminal, right? That is drain terminal, that is the gate terminal. Now can you help me populate various capacitance? Let us do the things which do not involve the bulk. So here what will come? So the capacitance to come here is GD. Then there is a capacitance that is going to come here, right? So there is a capacitance going to come, I can draw that here. So that capacitance is C. Here. Now we need a bulk. So I am going to draw a bulk somewhere here. Okay. Now for the purpose of a common source amplifier, actually the bulk is also connected to incremental ground. Okay. So the bulk is connected to incremental ground in a common source amplifier. Think about this. Maybe I will clarify this point later. Okay. Maybe we do the other amplifier, it will become clear, but we clarify this point later also. So basically you have this bulk which is connected to incremental ground, and you have the source which is connected to incremental, right? That's the way the amplifier is. Is that right? Does everyone follow that? Source, right? All of this is the source terminal, right? That is, so that is connected to incremental ground. Okay. Now can you tell me where the other two capacitance come? So I have a CSB which is coming from there to here. Is that CDB? No, wrong. So this is CSB. Where does my CDB come? Right? Now it's actively to ground, so I can connect it to this point also. Right? Yeah. So your CB in principle be connected from drain to, but then because bulk and source are effectively incremental ground, I connect it to between drain and source also. And as Shivang correctly pointed out, for the common source amplifier, I don't need to worry about CL because source and bulk are ground. Anything, no, two things are, it's a short, no, they are connected to ground. I can connect anything across it, trouble it, right? Okay. So effectively, I have this to be my that is my that incremental circuit, including the various capacitors. And this is CGD. Okay, what are you interested in? What is your VGS? Again, VGS is the same, plus minus VGS, and your output is taken here. Okay, now what are you interested in? So you are interested in what your interest finally is? I want VO VS, VO by S, right? And now because both these things are everything now is going to be a function of frequency. Instead of frequency, I will work in the S domain. So this whole thing will be a function of where S is what? J omega. Okay, or it could be in general it could be sigma plus omega. Right, could have a real part also. On the imaginary, it is j omega. Okay, I find out what this is. Is this E? Is this easy? In fact, it's not. It's quite messy. Okay, so we are going to do it systematically. Let's see what happens. First thing I am going to do that I want to identify how many nodes I have in this problem. How many nodes are there? One is the ground node. 6. Don't scare me. So all of this is one node. Correct? The next node. There is one node. Then okay. So in order to simplify this, as I said, there are 3 nodes. There is one node, I can number the nodes. So there is one node here, there is a second node here, there is a third node here, and all of this, the fourth node, which is the ground node, right? So we don't need to worry about the ground node. Can we eliminate this third node? Yes, indeed. We can do that by converting this voltage source and the resistance RS into its equivalent by finding the Norton equivalent of that voltage source and that resistance. So that is given by a Vs GS, where GS is 1 by RS. Your GS is 1 by RS. Okay, and I've drawn a GS here, which means that's the conductance. Similarly here, this is my GL. All right. So this particular, that green box becomes this green box, right? So this particular green box becomes that green box. Okay. So let's now analyze this particular circuit. Again, there are 2 nodes. This is node 1 and node 2, and that is your node 3. Right. So moving forward, in order to analyze this, we have to look at Kirchhoff's current law at the two nodes. So let me first look at node 1. So if I look at node 1, then just follow the arrow. So I can talk about the current leaving node 1 along GS. So that is Vx GS. Then I can look at the current which is leaving through CGS. So that is S times CGS times Vx. In order to simplify matters of notation, I am going to call this quantity as Vx, right? I am going to call that quantity Vx, and this similarly this quantity is going to be Gm Vx. Okay, just for fun, doesn't change anything. Okay, let's go back to Kirchhoff's voltage law. So yeah, okay, so that is leaving through the capacitor. The capacitance is Cg, so its admittance, right, is 1 by j omega c. The S domain is nothing but, sorry, its answer is j omega c, which in the S domain is S times Cgs, right. Then I look at the current leaving through capacitor Cg, and that's going to be S times Vx minus V0 times Gd, that's different, and current in the node, which is given by this current source, which is Gx. Okay, and I can look at node 2. For node 2, similarly, let's first look at the current leaving through G, that is V naught GL, then the current leaving through dB, which is done by times B times V naught, and the current leaving through CG, right, and that is this. This is just a negative of the current above, and the current leaving the current source, which is Gm Vx. So what we are interested in is this ratio of V0 by Vs, and as you find here, there is a Vx involved. So our aim is to express Vx in terms of